So, all set to go at last.
I'm gonna try my video again. It might work, it might not.
Oh, okay. All right. I want to make sure it's recording. Yep, it's recording. Okay. Yeah, I briefly saw you on video, but
Okay.
yeah.
Did it go out?
Yeah, it just went in and went out right away. Okay, so we have a little time. Questions on the homework?
I've been in the math room since 9 this morning, Floyd. For those who don't wake up till 1.
That's right. That's pretty great.
Okay, so homework questions.
Number 3. So what we were just talking about.
So that this actually is a norm. Okay.
So we need to show those 3 properties are true.
Yeah. Yeah, so you had to show, for instance, that the C norm of X equals 0 if and only if X is 0. And now one important assumption that you're given about C is, now C is m by n, but the rank of C is actually equal to n. Without that, this isn't true. And actually, since this is an if and only if, of course you got to go both directions. One direction is pretty straightforward, the other somewhat less so. But what you're doing in all 3 conditions, because that's one thing, and then you have the other conditions, like if you scale the vector, you scale the norm, and so forth. And then the third one being a triangle inequality, which I won't write out here. But basically you're piggybacking off the fact that this is a norm. This, now this is any vector norm. It's deliberately not specified because you're not supposed to use any information about it except for the fact that this norm, without the C, already satisfies these conditions. Okay, so see what you can do with that. Other homework questions? Or from down there? Okay.
I do have, can you say what you just said again about the norm? This is the norm without the C. What?
Okay, because here, with this norm with a subscript C, so that's what you're actually trying to show as a norm, but this is defined in terms of some established vector norm. For example, like the 1 norm, infinity norm, 2 norm, whatever. It's deliberately not specified which norm that is because you're not supposed to use any specific properties of it. The only thing you know about this vector norm, so in other words, anytime you're, so the one without the subscript C, is the fact that this norm already satisfies this condition. You're going to take advantage of that to show that this also satisfies these 3 conditions.
Okay.
Yeah. So really what you're going to do is, all 3 of these conditions are written in terms of the C norm. The first thing you ought to do, in most cases, is write that, you have some expression here involving a C norm, write it in terms of a regular norm, work with that, and then put it back in terms of a C norm.
Okay.
Yeah. Yeah, free is one of the ones that tends to throw people for a loop. Okay. Other ones from the homework? Okay. So this is due Monday. So for those of you who are not right here in Hattiesburg, you can just well, it's up to you how you want to do it. Like you can send pictures and email it to me. That'll work. Because the usual system from the coast of using campus mail is a little slow. So we'll do everything electronically.
So do you want to scan, so like if you scan it in and then email it to you as a PDF?
You don't have to do it that way. Like for instance, if you just like took pictures of each page and sent all those to me, I could easily look at it on my phone.
Okay.
Yeah.
I
So,
did that last year for my.
Oh, wow,
I took
okay.
yep. so yeah, that'll work. Okay, so we're good on homework at least for now. I hope again everybody has got a good start on it at least. Okay. I don't have my notes. I will grab them. Okay. All right, so now we are getting into solving systems of linear equations, where we start with techniques that you learned in class such as 326, but then what has to be done differently because it's a computer that's doing a job, and the presence of round-off error is going to have some significant influence there. But first, you need to make sure that everyone is on the same page as far as sort of things you would have learned in linear algebra. Okay. So, the kind of problem we're focusing on here, solving system linear equations, ax equals b. A is a real n by n matrix, so the square matrices that are invertible. Okay. Now, who remembers from your first linear algebra course, what is the process you go about in that kind of class? You're given matrices are like 3x3, 4x4, whatever. How did you go about actually solving such a system? What's like the first thing you would do? Gaussian elimination. Gaussian elimination involves row operations. And the row operations, there are three kinds of row operations. Okay, so one of them is you multiply a row, so you scale a row of the system, so you're multiplying both sides of the equation by a certain constant. That one's not going to be really needed for us. Another is to interchange rows. And the third and by far most useful operation is add a multiple of one row to another. Okay, now, so you have to do all these kind of operations in a class like 326. In numerical linear algebra, the usage is somewhat different. Certainly, at least for the first two operations, because, and this terminology will likely ring a bell with you, but it's definitely good understanding if you've forgotten it. When you are performing Gaussian elimination using row operations, what was the goal? Like to make the matrix, put the matrix in what form? Well, what?
Triangle or diagonal.
Yeah, and the way it's normally called 326 is row echelon form, where the matrix is upper triangular, and then they would have you do reduced row echelon form, where actually where you have the ones in the diagonal, and basically you're basically reducing matrix to identity on one side to reveal the solution on the other. And then you do the same thing to invert the matrix. So that involves scaling rows to make the diagonal entry a 1. We don't care about that. So in fact, we might as well kind of forget that this operation even exists for the most part. We'll bring it back later for strictly numerical purposes much later on. Interchanging rows. Why would you need to, why would it be necessary to interchange rows when you're solving a system? Yeah, and when you're solving problems by hand, that is the only time you would need to do that. Numerically, you'll see that it needs to be done much more often in order to contain a round-off error, to do all the other operations that are being performed. This operation will serve the same purpose as in 326, just to try to eliminate variables from equations and get that row echelon or upper triangular form. I guess it's pure mathematicians who like to say row echelon form and numerical analysts to say upper triangular. So that's the one I'm going with. Okay, so what I'm going to do is I'm going to, and this is largely be a review, but to illustrate the process in a simple example, and then take that and be able to state an algorithm of a kind that would be relatively easy to write code for. Whoa! That could have been disastrous. All right. All right. So our example, just this system of linear equations. Plus 1 plus 2x2 plus x3 5. Okay, but first thing we want to do is write this in matrix vector form. So A will be the coefficient matrix, so 1, 2, 1, 3, 2, 4, and then 4, 4, 3, and then the vector B will be the right-hand side, 5, 17, and 26. And whatever we do to one side, the matrix, we have to do to the other side, B. So in 326 type classes, it's customary to put A and B together. So I'm like adding A onto B as an extra column. And I'll just put this line here to separate them. But now we're basically working with a 4 by 3 matrix. What is this matrix called? Augmented matrix. Now I'll use it just for this one example, but in a numerical implementation, we don't actually use an augmented matrix, but it'll take us some time to get to that point where we can just do away with it. Because really the best thing to do is think of A and B as separate for efficiency's sake. Okay, so what we can do now is do row operations on this matrix, and we're going to go about this in a systematic manner. We want to reduce this to upper triangular form where the only non-zero entries are in this triangle here. We need to eliminate these guys. So the process is we work from left to right. We go first column, go from top to bottom, then move over to the next column, top to bottom, until all those entries below the diagonal are gone. So, so the first row operations, so we'll need 3 of them in this case. So, so I'm going to I'm working on the second row is going to be itself minus 3 times the first row. And I'm using 3 because this entry is 3 times this one. So it's a ratio of the two that matters. So in fact, I'll just write in that ratio explicitly so you can see where it comes from. So it's entry you want to eliminate divided by the diagonal entry you're using to eliminate it. So this is our first row operation. We're subtracting 3 times row 1 from row 2. And we're doing this all the way across the augmented matrix. So as a result, our augmented matrix becomes, so first row is not going to change at all. Second row, we'll get a 0 here, and then we have minus 4, 1, 2, and then we haven't done anything with the, actually I'm going to hold off on writing that next row in because we can do the same thing to eliminate this entry here. Row 3 is equal to itself minus the entry we want to eliminate, the 4, divided by the corresponding diagonal entry, which is a 1, times R1. So we're always using a multiple of R1, row 1, to eliminate something in the other rows. So when we do that, that's going to cause this entry to become 0. And then we'll get minus 4, minus 1, and 6. Okay. So the other entries in, like on the right-hand side and over here, are affected by these other entries being multiplied by 3 and then later 4 and subtracted from rows 2 and 3. So, so we're working on these entries to try to eliminate them, but that causes modifications to the other ones. Okay. After that, we only have one operation left, that is to eliminate this entry. So row 3 is going to be itself minus the entry we want to eliminate, minus 4, divided by the corresponding diagonal entry, which is minus 4, times row 2. So really we're just going to subtract row 2 from row 3, because the ratio of entries here is just going to turn out to be 1. So we'll go one step further and get a upper triangular system. Then 0, 0, minus 2, and 4. Okay. So now everything below the main diagonal has been zeroed out through these row operations. So here we worked in the first column, and then here we did one last row operation to deal with the second column. So now that the system is in this form, why is it now easier to solve? What can we do? Back substitution, but for those who are not familiar with the term, what is that?
Take the bottom. Yeah. Take the bottom.
Yeah, here, if we were to think of this as a system of equations again, so go back to this notation, that would be minus 2x3 is equal to 4, minus 4x2 plus x3 is equal to 2, and then x1 plus 2x2 plus x3 is equal to 5. So now, because there's only one unknown in this equation, that's trivially solved. So x3 is equal to minus 2. And now we can plug that value into this equation. So x2 is equal to, okay. All right. So x2 is equal to the right-hand side value. And then this term, minus x3, we subtract that off. And then we have to divide by the coefficient of x2, which is minus 4. So that's going to give us minus 1. And then we take x3 and again substitute it in here. x2 gets substituted in here. So now we have x2 and x3 substituted in the first equation. Now we can systematically solve for x1. So x1 is going to be 5 minus 2x2 minus x3. So all these other terms we're moving to the other side. And then we divide by the coefficient of x1, but that's just 1 in this case. And we get 9. So now we have our solution. X is equal to 9 minus 1, and minus 2. By the way, I should mention that it's kind of a pain to have an example of Gaussian elimination, these row operations, and substitution in which the numbers are integers at every step of the way from beginning to end. Actually, 3 by 3 is not so bad, but I have a 4 by 4 example later in the notes, and I'm never doing it again. It's like put up a fraction. I mean, having an integer solution and original matrix integers, that's easy. But having it every step in between, it's tall order. Okay. So here's a general process that we find these ratios of entries, see what multiple of each row to subtract from other rows to eliminate the entries we need to get rid of to get this upper triangular form. Then we can start from the bottom and work our way up, where we take our right-hand side value. Actually, I'll write out in full what's happening here. So this is 4 over minus 2 is minus 2. So our right-hand side value minus terms we move to the other side that involve unknowns we have already computed. And then we're always dividing by a diagonal entry in order to get the unknown value. So what I want to do now is describe this general process of both the elimination and the substitution as an algorithm that one can implement in MATLAB or programming language of your choice. So any questions about the process? I mean, this is all kind of 326 review. Okay. Oops, something went wrong here.